Raw data is messy, and models need a little help to find the signal in the noise. That's what feature engineering is all about. It's the art and science of transforming your raw data into features that truly make your model shine. Let's dive in.
You get this amazing new dataset, and it has hundreds, maybe thousands of columns. And your first instinct is probably, yes, more data is always better. But in the world of machine learning, that can be a serious trap. It just sounds wrong, doesn't it? But it's true. Having too many features can absolutely torpedo your model's performance. It's kind of like trying to have a conversation in an incredibly loud, crowded room. The more background noise there is, the harder it is to hear what the person in front of you is actually saying. Your model feels the same way about noisy features. Now, this problem has a really cool, kind of scary-sounding name, the curse of dimensionality. The more dimensions or features you add, the more sparse and spread out your data becomes. It makes finding meaningful patterns like searching for a needle in a haystack that's constantly growing bigger and bigger. Our job is to shrink that haystack. So, how do we fight this curse? Well, our first line of attack is feature selection. Honestly, the best way to think about this is like you're a coach picking the starting lineup for a sports team. You don't want everyone on the field at once, right? You want your absolute best players, the ones who will actually help you win.
One of the fastest ways to start picking your team is with what we call filter methods. This is like doing a quick scan of every player's individual stats before the game even starts. You're just looking at each feature one-on-one and seeing how strongly it relates to your goal, what you're trying to predict. It's a super quick way to get a first impression of who your star players might be.
And the biggest advantage of filter methods is that they are incredibly fast and don't require a lot of computing power. But they do have a pretty big blind spot. They only look at each player in isolation. And as any coach knows, sometimes two players who look average on their own are absolute magic when they play together. So, to see how the players actually work as a team, we can move on to wrapper methods. Now, we're not just looking at stats anymore. We're actually running drills. We're wrapping our model around different combinations of features and having it tell us which lineup performs the best. It's like a practice game to find the winning combination. Now, the trade-off here is pretty clear, right? It's power versus time. Wrapper methods are amazing because they understand how features interact and can find the dream team for your specific model. But man, they can be slow. And there's a higher risk of overfitting, which is like finding a team that's amazing in practice but completely falls apart in a real game against new opponents. Okay, so what if we could get the best of both worlds? That's the promise of embedded methods. With these techniques, feature selection isn't a separate step before training. It happens during the model training process. It's like having a brilliant coach on the sidelines who is making adjustments to the lineup in real time as the game unfolds. Embedded methods really hit a sweet spot. They give you a fantastic balance of performance and efficiency. They're generally more accurate than filter methods and way faster than wrapper methods. The only real catch is that sometimes it's hard to ask the coach why it made a specific decision. The reasoning can be a bit of a black box. Okay, so let's put it all together real quick. Filter methods, those are your fast, low-cost initial scan, perfect for huge data sets. Wrapper methods, they're slow and expensive, but they can give you the best possible accuracy, especially on smaller data sets. And embedded methods, they're your balanced, integrated approach. All right, so up until now, we've been acting like a coach, just picking from the players we already have. But what if we could go into a lab and create a new superstar player from scratch? Well, that's basically what feature extraction is. It's all about combining our existing features to build new, more powerful ones.
And let's be super clear on the difference here, because it's a really common point of confusion. Feature selection is about choosing the best of what you already have. You just end up with a smaller set of your original features. Feature extraction is about transformation. You're creating brand new features by mashing up the old ones, often ending up with fewer but much more meaningful features.
By far, the most famous way to do this is with something called principal component analysis, or PCA. So imagine you have two features that are telling you pretty much the same thing, like a person's height in inches and their height in centimeters. They're highly correlated. What PCA does is find a way to combine them and other variables into new, uncorrelated features called principal components that capture the most important information, or variance, in your data. It's all about summarizing your data and cutting out the redundancy. We have selected our team. We may have even created a few new superstar players. We are almost ready to play. But there's one last crucial step. Before we send our features out onto the field, we have to make sure they're all playing by the same rules.
And that's exactly what feature scaling is for.
Think about it. What if you have one feature for a person's age, which might range from, say, 18 to 80, and another feature for their annual income, which could be in the hundreds of thousands? To a machine learning model, those big income numbers might look way more important than the small age numbers, just because of their scale. Scaling puts all your features into a common language so they can be compared fairly.
And there are two main ways we do this. The first is normalization, which squishes all your values into a fixed range, usually 0 to 1. This is really useful when you know your data has a bounded range. The other is standardization. This rescales your data so it has a mean of 0 and a standard deviation of 1. This method is generally less sensitive to outliers and is preferred for many algorithms.
So how does normalization actually work? Well, the formula looks a little complex, but the idea is simple. For every value, you subtract the minimum value of that entire feature, and then you divide by the range, which is just the max minus the min. That's it. Every single data point now sits somewhere between 0 and 1.
Standardization is a little different. Here, for each value, you subtract the average value of the feature, and then you divide by the standard deviation. What this does is it centers your data right around 0. So a positive value means it's above average, and a negative value means it's below average. A lot of models really like this.
Phew, that was a lot of work, right? Selecting, extracting, scaling. So the big question is, was this whole journey worth it? And the answer is a resounding yes. By taking the time to properly engineer our features, we have set our model up for success in so many ways. Let's look at the payoff. The benefits here are massive. First and foremost, you get better model performance, higher accuracy, better precision. Your models will also train so much faster because they're not wading through junk data. You'll reduce that risk of overfitting we talked about, meaning your model will actually work well on new data. Plus, simpler models are just easier to understand and explain to people. And you'll save on compute costs. It's a win-win-win-win-win.